Your files live under hurricane winds, in a desktop hard drive spinning at 7,200 revolutions per minute. The surface rushes by at roughly 35 to 40 meters per second near the rim. That is about the wind speed of a Category 1 hurricane. A redhead flies a couple nanometers above that surface, never touching it, and still gets perfect bits. How is that even possible? Picture a tiny surfboard gliding over a glossy mirror. The head sits on a little block called a slider. As the disc spins, it drags air along with it. That moving air lifts the slider just enough to fly. Not meters, not micrometers. About 1 to 3 nanometers. That gap is thousands of times thinner than a human hair. Now add pressure. The head is not skimming gently once. It reads and writes while flying, all the time, over billions of bits racing under it every second. It must aim at the right track, at the right microsecond, and pull a clean signal out of noise. And it must do that without ever scraping the surface. Here's the core problem. We want to pack trillions of bits into a few square inches. We also must never let the head touch the platter. Signals get weaker fast with distance. This is called spacing loss. Even a tiny extra gap makes the read signal fall off hard. That is why the flying height has to be outrageously low. Now think about dust. A smoke particle can be 100 to 1,000 nanometers tall. The head's flight path is 1 to 3 nanometers. A dust speck in that gap is not a speck, it is a boulder. If the head hit it at hurricane speed, bad things happen. We will come back to that. One more simple way to feel spacing loss. Hold a magnet near a fridge note and pull back a millimeter. It weakens a lot. This head is doing the same trick, but with fields from tiny magnetic grains, and with a gap that is smaller than the thickness of the fridge magnet's paint. Hard drives did not start here. In 1956, IBM's RAMAC stored about 5 megabytes on 50 platters the size of pizzas. The cabinet was as big as a fridge. Today, one single 3.5-inch platter can hold hundreds of gigabytes to multiple terabytes. The whole drive fits in your hand. What changed was how many bits we can pack per square inch. With perpendicular magnetic recording, common since about 2005, areal density rose to around 1 to 1.5 terabits per square inch. Roadmaps with heat-assisted writing push for several terabits per square inch. Same size disk. Wildly more bits. The platter is a layer cake built for bits. At the core is glass or aluminum for stiffness. On top of that sits a magnetic alloy made of tiny grains. Over that is a carbon layer only 2 to 3 nanometers thick. Then a lubricant film about 1 nanometer thick. That last slick layer helps if anything ever gets too close for comfort. There is a clever trick in how data is laid out around the circle. The outer edge is racing faster past the head than the inner edge. So the outer tracks get to store more sectors per lap. That is called zone bit recording. It gives something like 30 to 50% more data near the rim than near the hub. Here's the part that feels like magic. The head flies because the disk spins in air. The drive is not airtight on purpose. There's a tiny vent with a filter that lets pressure equalize with the room. The spinning surface makes its own little wind. The slider's shape is like a tiny wing that rides that wind. To pick the right track, the arm swings on a pivot, just like the cone in a loudspeaker. A magnet and a coil create force. That is a voice-coil actuator. It can move the head across the disk in a few milliseconds. Then it keeps nudging the position every few microseconds to stay centered. Engineers also trim altitude mid-flight. Inside the slider is a little heater. Warm it a tiny bit, and the slider bulges out by a couple nanometers. That is enough to fine-tune the flying height for the current temperature and pressure. It is like raising your seat by a hair so you just clear the table. Writing and reading are two different jobs. Writing takes muscle. A tiny coil feeds a strong field into a sharp right pole. That field forces a microscopic region on the disk to flip its magnetic direction. The spot is small and very controlled. The head is drawing arrows on metal grains at highway speed. The industry changed the direction of those arrows. With perpendicular recording, bits point up or down into the surface instead of lying flat. That packs the bits closer, without the neighbors fighting each other. It sounds simple. It took a lot of material science to make it stable on a hot spinning disk. Reading is all about sensitivity. The read element is not the same piece as the write pole. It is a tiny sensor that changes its electrical resistance when a magnetic field changes near it. That effect is called magnetoresistance. The giant and tunneling versions let the sensor feel fields that are incredibly small. The change is tiny, but it is enough. Staying on track needs a guide. Before the drive ever leaves the factory, special equipment writes servo marks in wedges around the disk. As the head passes each wedge, it reads a pattern that tells it if it is left or right of center. The controller uses that to steer back to the middle of the track. Timing matters too. At 7,200 revolutions per minute, a full spin takes about 8.3 milliseconds. On average, you wait half a spin for the right sector to come back, so about 4.17 milliseconds. Seeks across the disk add 4 to 10 milliseconds, depending on how far the arm moves. The readback is not a stream of clean ones and zeros. It is a wiggly analog signal with noise and jitter. The channel uses math to turn that ripple into bits. First, it predicts the most likely pattern of transitions. Then it uses strong error correction to fix the remaining mistakes. The result that reaches your computer looks perfect. Old drives split the disk into little blocks of 512 bytes. Modern disks use 4,096 byte sectors most of the time. Bigger sectors shrink the overhead and leave more room for stronger correction per block. That helps both capacity and reliability. Here's a fun twist. The raw error rate inside the channel is not tiny. If you looked in the middle of the process, you would see lots of small errors. The error correction code wipes almost all of them away. Vendors specify that the chance of an uncorrectable error that reaches the operating system is extremely low over huge amounts of data read. We are not done pushing limits. One path is shingled magnetic recording. The right head draws a new track that partly overlaps the previous one, like roof shingles. You get more tracks per inch. The catch is that random rewrites can force a bunch of shingle rework. It is great for big sequential storage and trickier for random edits. Another path is heat-assisted recording. The head adds a tiny laser that warms a spot by a few hundred degrees for a few billionths of a second. In that instant, the medium is easier to flip. Then it cools and locks in hard. That lets the grains be more stable at room temperature, while still writable in the hot moment. This thing is delicate, yet it is built to survive years of use. Do not open a drive on your desk. One airborne speck can land on the surface. The head can hit it and carve a bright arc through billions of bits in milliseconds. Drives park the heads on safe ramps when off. The controller also manages altitude as temperature and air pressure change. And that tiny vent with a label really matters. Block it, and the air bearing can misbehave. Step back and reframe the scale. On a square inch, roughly a trillion bits stream under a head that flies lower than a smoke particle is tall. All of it happens at hurricane-like speeds, with constant nudges to stay on track, and heavy-duty math cleaning the signal in real time. Your files live on a flying, self-correcting machine that dances a couple nanometers above a mirror. If this kind of inner machinery clicks with you, you will like the rest of Buildguts. Subscribe and give this one a like if it helped. There are more calm, satisfying, "oh, that is how it works" videos waiting on the channel. Thanks for watching, and see you next time.